Hi everyone. So in this video, we'll just give an overview of the regularization strategies that we'll consider in this section of the course, and most of them we'll discuss in detail later. So we presented in the last video norm penalty regularization, right? Which basically consists of adding to the maximum likelihood estimator cost a regularization coefficient times a regularizer that depends on a norm of the parameters theta, and we said that it's mostly a function of the weights, not the biases in most cases. Now, one problem with norm penalties is that even though it penalizes the norm, it's continuous, right? And it doesn't have a hard threshold. So it might allow some weights to grow up, like you really don't have a guarantee on the limit, regardless of what the regularization coefficient is, as long as at the cost of making other weights very small, right? So the problem here is that there could be many problems. It could lead to unstable optimization because of weights exploding in magnitude. It could lead to some weights overwhelming the learning process, making other weights or other units or other complete layers have negligible effect on the cost function. And all this could be problematic in both for the optimization strategy as well as the final solution that we obtain. And that's why an alternative strategy, if these issues arise, is to have constrained optimization, which is basically putting a hard threshold on the norm. And you could also have a combination. You could have a hard threshold on the norm as well as a penalty as long as the norm is within the range. But the important thing is that now you guarantee that the norm of the weights is within a certain range. Now you could further apply this constraint on weights within a layer, or weights emanating from one unit, or weights sinking in one unit, and so on. Right? And every variant of applying this strategy will have a different role. Now, the disadvantage is that this also deprives you from a flexibility that the norm, the original norm penalty regularization has, and that can prevent you from reaching good solutions. Maybe the optimal solution has a large discrepancy between the weights, and some weights have to be very large, and others can be very small. Regular norm penalty would allow you to do that. Constrained optimization with a hard threshold would not allow you to do that. And sometimes in the literature you would find this form of regularization called explicit constraints. Regularization with explicit constraints. One other category of regularization strategies that we'll discuss is noise injection, which is basically artificially injecting noise. You could inject that noise at the input. So you have the input vectors, the x values. You could add some noise to them, or you could add it to the hidden units or the output units, right? Each of these has a different objective. When I add and reflects a different belief. So when I add noise to the input, that reflects my belief that the training data, the input is coming from a noisy data generating. It's not exactly the original, the true data generating process, but there is noise in the process, right? For example, my input could be received wireless signals, right? Received wireless communication signals. And I could know, like an expert my domain knowledge can tell me that this received signal already experienced noise over the channel or over the air. So I don't want my learning to be sensitive to this noise. So what I do is that I artificially add this noise to the input, right? So I add extra noise to the input such that the network learns that it becomes insensitive to that noise. And this is related to the next type of regularization strategies that we will cover, which is dataset augmentation. This is one kind of dataset augmentation, is to add noise to the data that you have and have many variants of that data with the added noise. In general, dataset augmentation refers to incorporating the domain knowledge about the invariance properties. For example, I have an image, right? and an image of a pen like this, right? And I want the network to realize that this is a pen. I want it to realize that this is a pen even if I rotate it like this, or I rotate it in the opposite direction, or more angle, right? So I know that I should be invariant to the property of rotation, so I augment the data with various rotation. Whatever image I have, I augment it with various rotations. In the wireless communication example, I know that there is noise over the channel, so I add noise. Now let's go back before we forget to the noise injection. Now adding noise in the hidden units could be very different, right? Because I want the network to be insensitive to the exact values of the hidden units, right? So that means that reflects a belief that I have, that the model that I'm designing or the neural network that I'm designing is not carrying out an exact computation. For example, if I'm believing that the first layer is doing some kind of edge detection, then I believe that this is not happening exactly. So I want the network to not be sensitive to the exact value. So I add noise to the hidden units while the training is taking place. Now I could also add noise to the output units or to the labels, right? So to the labels, this would be called label smoothing, and we'll discuss it later in that section. And that basically reflects a belief that the labels that I have might be noisy, right? So for example, I ask many people to label images by hand, manually, right? So I don't have full trust. I know that 95% they are accurate, but I don't have full trust in the output that they give. So basically I flip that output, or I add noise to it with a certain probability, right? So that the network can learn not to become extra sensitive to that label data. Now another class of strategies is early stopping, and we'll discuss that actually in detail, and we'll draw analogy to between early stopping and L2 regularization. And early stopping basically relies on you take part of the training data and you save it as validation data. You never train with this data, and you monitor the error of this data while you're training. And typically you would have a U-shaped validation error. So at the start, as you're minimizing the training error, the validation error also goes down. And then the validation error starts to goes up while the training error is going down. We say that this is an overfitting regime. So early stopping relies on finding basically the bottom of the U. So that when it starts to go up, I go back to the last parameter setting at the bottom of the U. Now, the next class of strategies we'll discuss is what's called ensemble methods, which basically relies on employing more than one model and then taking the opinions of all these models. So one possibility is what's called bootstrap aggregating or bagging. And bagging basically refers to making multiple models or even one model with different data sets sampled from the original training set. And we'll discuss it in detail. And that randomization in the training set creates diversity between the models. And another class of ensemble methods is called boosting, and the difference is that you can imagine bagging as doing diversity in parallel, boosting is doing it serially. So while I'm training, I am changing the model or changing the data set, selecting the next sample based on what happened in training so far. And last but not least, we'll discuss dropout, which is a very important technique for regularizing deep neural networks, which basically relies on randomly dropping hidden units while training. And you can view this as multiplicative noise injection, multiplying by a binary noise, 1 or 0. If it's 0, then you remove the hidden unit. If it's 1, then you keep the hidden unit. And you could also view it as bagging, which is a very interesting analogy that we'll discuss in detail. You could view every realization of the network with dropout as one model in the bagging algorithm. Thank you.